Welcome back to AI in Medicine. In this first lecture of part 4, we are going to review a few key concepts. In previous lectures, we've often referred to the term data set split, and in this slide, I just wanted to offer you a visual representation of what I mean. And so you can see here on the left, this represents the entirety of your data. And in this case, I've made it such that each entity in your data set is a different color. We then shuffle the entire data set at random, and then we split it. And most often, you split into three sections. The first two is your training set and your validation set, and this is what you use in order to train your algorithm. So you basically repeatedly or iteratively train and then validate, make some changes, train, validate, make some changes, train, validate, and we keep doing that. And once you're happy with your training, you then want to provide people with a confident test. And so you have retained a section of your data set that you have not looked at, you've never used it, you don't know what's in it, and then you use your new trained algorithm in order to test and then to provide basically diagnostic accuracy. So how good is your algorithm based on this one single test set? This doesn't mean that you then go back and retrain. It's done once you've use this final test set. That is to report the final statistics on your algorithm. Of course, down the road, you can always retune your algorithm by using a brand new large data set and repeating this entire process in order to improve your algorithm. As we saw in the previous slide, the data split provides you a way in order to deal with this challenge of developing a model that is both not overfitting and not underfitting. And this is just a visual representation. Once again, we've discussed it in the past. An underfit model will be a biased model, meaning that the estimates in your model, the coefficients, the parameter estimates in your model will be biased because it is a simple model. And in order to achieve that simplicity, you basically bias your estimates. And so you have high bias in an underfit model. On the other hand, the more you overfit your model, or the more you increase the variance in the model, so all the little changes per data point in respect to your model is variance. And the more you increase the variance in your model, the more it's going to be an overfit model, which basically means that your model is memorizing your data set. It is taking into account every deviation of a single data point to the model and accounting for it, and therefore can memorize it. And a perfectly overfit model will have 100% accuracy because it literally can recognize every single individual data point. Now, that is a high variance model, and what you want to do is, of course, find the happy middle ground where you are balancing bias and variance. That's the bias variance trade-off, where you basically come to an agreement between the two, where you have a model that is generalizable, so meaning that the variance is lower, however, is useful for you, and where the bias is minimized, meaning we're minimizing the error in your model being able to predict. And that is the underfitting versus overfitting story. Here's a way of looking at the impact of overfitting, underfitting on your model training. So on your y-axis, you have accuracy. On your x-axis, you have time, which will be your epochs or epochs, meaning as you train iteratively your model, your accuracy will go up because it's learning, and that's over time. And time in this case, as I said, is iterations of training. And you'll see that the training accuracy, so how accurate was your model in the training session, is the blue line. And then when you validate, so you run your model on the validation split, you'll remember we have 3 splits: training, validation, and test. We're only using training and validation. When you use the training split, you have the blue line. When you then follow it up with the validation split, that's the red line. And what the difference between the red and the blue line represents is overfitting, meaning if the 2 lines are distant from each other, then that represents some overfitting. If the 2 lines were superimposed, then you would have no overfitting. And that's where you can assess whether or not your model is overfit. Inevitably, you're thinking, well, okay, how do I deal with the bias? Well, if you have the 2 lines that are superimposed, you're like, oh my God, that's amazing, there's no overfitting. However, your accuracy is just crap. That is most probably indicative of a biased model. So meaning that there's no overfitting because it's so simple. However, the ability to predict has been impaired because you've simplified it so much that the model is no longer able to predict accurately. Now, for those of you who took my biostatistics course, you might be thinking, that split into 3 sections, training, validation, and testing, is done at random, right? Because you shuffle your data randomly and then you split it into those 3 sections. You might be thinking, I understand that if data, for instance, is distributed normally, you have on the tails, each tail, the very low probability of obtaining an extreme value. So what if that split results in some kind of weirdness? So extreme value in that sense for your split. Well, of course that can happen. And if that's something that concerns you, which it should, then you can consider doing what's called cross-validation. So in this case, you shuffle your data set, you split it. In this case, though, you split it into more than the 3 sections you want for training, validation, and testing. You actually split it into folds, and that's called it's called cross-validation k-fold. And in this case, for instance, let's say we were to split it into 4 folds. You would then, in order to do the training validation, you would take 3 sections for training, 1 section, and then validate it against 1 section, and then shuffle them all up again, and take 3 sections again, and 1 section validation, shuffle it again. As you can imagine, there are only so many ways you can shuffle them, and once you've exhausted that, then you will have, in the end, a number of scores, depending on your splits, that you can then average and produce the standard deviation. And inevitably, what you're looking for is consistency. So you're looking for, accuracy scores that are close together and that produce a small standard deviation. The larger the standard deviation, the more the data, the way the data is partitioned or split, is impacting your ability to train. And that's not a good sign. That usually indicates that you are, in need of more samples, meaning a larger sample size, because for a variety of reasons, but maybe the most obvious one is that you have heterogeneity in your data. So this is what we call cross-validation. Does it mean that you should not partition off a test set as well? Absolutely not. I think you should as well. So let's say from the beginning you would partition your data into, let's say, a working set and a test set that you never touch, and you put it away and you lock it away and you never look at it. And that working set, you can then do cross-validation with it, and you can split it into however many folds you want and repeat the process as much as you want. And then you end up being able to report your average and standard deviation from your cross-validation. You can even report a coefficient of variation as well. And then you then do the test, and then you can report the accuracy, the final accuracy from your test set, which is always very nice to do. Here's a simple three-fold cross-validation example. We start with 3 sections or 3 folds, the top 2 for training, the bottom for validation. We then shuffle them, and the top fold is for validation, the bottom 2 for training. Of course, the last combination possible is the middle section or the middle fold for validation and the top and bottom for training. Inevitably, the more you increase the number of folds, the more computationally heavy your work, meaning that you have to calculate, you have to run the training and validation of your model on the data for the amount of different possible combinations. And let's say you get to 10 or 12 or 15 combinations. Well, you'll be running your GPU for a long time to get those numbers. Now, though it's wonderful if you have a very complex algorithm with a very large data set, it may actually be prohibitively difficult for you to perform, and therefore it will limit the number of folds that you can consider. So the next key concept is evaluation metrics. And in this case, we're going to start off with classification. So we're going to look at the classification accuracy on the test set versus the training iterations. So if you look on the x-axis, you have the training iterations, so the number of times we've gone through the training process. That this can also be considered epochs or epochs. On your y-axis is the accuracy as measured between 0 and 1, with 1 being 100% accuracy. And how do we calculate accuracy? In this case, it's very simple. It's the number of total correct classifications over the number of total classifications. Now, you will remember from your medical student days the lecture on diagnostic accuracy, where you took a 2x2 table and calculated sensitivity, specificity, positive predictive value, negative predictive value, odds ratio, relative risk, all that fun stuff. Well, it's no different in the world of machine learning. It's just that we call them a little differently, and then we have a few other metrics that we use in order to improve our algorithms in such a way to meet the specifications. So in this case, precision here, you can see on this slide, is the same as sensitivity. The bottom one is specificity. So those are the two that you probably know the best from medicine. Now, accuracy, interestingly, is not something that is often reported in medicine, but it is the go-to metric for machine learning. Is it appropriate to only report your accuracy? No, I wouldn't. If you are reporting your algorithm in a medical context, then I definitely recommend not only reporting your accuracy, but also your sensitivity and specificity, or your precision, if you wish, and specificity, because that makes sense from a medical standpoint. And then you're going to want, if you would like to report an overall fit as a diagnostic test, for instance, then you can report your area under the curve. In the case here, you'll see that there's recall and F1. Now, these are just two other metrics that provide you with basically a tool in order to measure and train your algorithm to best fit, once again, certain specifications. So the F1 is kind of a combo, if you wish, between precision and recall. And it will allow you, for instance, to better hone in on your algorithm's probabilities for selecting a specific class. So it'll allow you to provide or to create a better algorithm if you're specifically interested in providing the probabilities. If you're just going to, have a threshold and it doesn't really matter, then you don't need to necessarily look at the F1. But if you would like to see what the probability is for a given class from your model and basically optimize for that, then you're going to want to, you'll be interested in using the F1. Now, what if you are performing regression? So you have a continuous dependent variable as opposed to a classification problem where you're just trying to choose between two levels in a binary problem or more than two levels for categorical. In this case, your outcome could be as simple as a weight. Let's say you would like to be able to predict someone's body weight based on input parameters, and it's a complex problem, so you've chosen machine learning. How would you report your success, or on the flip side, your error? Well, there is the mean squared error, and this is often used and reported. However, there is more penalization to outliers when you use this calculation. There's also the mean absolute error, and this one is used often when there are outliers and you would like it to be a little bit more robust to outliers, meaning less impacted by a few outliers. And then you have the root mean squared error, and this is nice because it provides your error in the same units as your target, which is often useful if someone would like to appreciate what the error represents in context. So we're now going to move from key concepts to maybe some helpful definitions. And in deep learning, we use something called frameworks. Now, what is a framework? So it's essentially a library, and a library is a compilation of functions in the world of machine learning that forces you, the user, to write code in a specific way. Now, in order to use this deep learning framework, you have to first transform all of your data into what's called tensors, which is a math term, and it's a matrix of matrices. You'll also recognize tensor because of the framework from Google that's called TensorFlow. So you can kind of consider frameworks as flavors, if you wish. They're machine learning coding flavors. Now here, this is a little bit dated, but it hasn't really changed much, and that's the deep learning frameworks from a few years ago. You'll recognize the more common ones from Google, for instance, which is TensorFlow and Keras. And then the one that we use, for instance, in our lab almost exclusively is PyTorch, and that came from Facebook. Some of the ones from Microsoft tend to be, and Amazon for that matter, tend to be very specific, meaning that if you're working in machine learning and deep learning in the areas that are going to leverage Microsoft and Amazon resources, then you're going to use their frameworks. In our world, in research, it tends to be TensorFlow, Keras, and PyTorch at the moment, and PyTorch is, in my opinion, probably the way to go in the medical imaging world. The next definition we're going to tackle is transfer learning. I'm sure you've heard it many, many times, doing transfer learning on a deep learning project. Essentially, it's when you use an already trained model, so you're using the weights that are obtained from an already trained model as a starting point or a base for your data set. And what it does is it can reduce overfitting on smaller, relatively smaller data sets like yours, for instance, in machine learning, in medical imaging. And these models are also known as the back model. And are they useful? Yes, absolutely. Should you be considering them? Absolutely, because it's a great jump start for you to be able to get into machine learning when you are limited by the number of images because of, let's say, cost. Acquiring, MRIs, for instance, is like about $500 each. and you need thousands. Well, that's a lot of money. How about if you are working with a relatively rare disease? Well, even if you have all the money in the world, you're just not going to have the number of patients you need in order to train a very successful model. So by using transfer learning, you get a jump start, because as you know, it's an iterative process. And so if you've already started ahead of in your training, then that is basically, it's more forgiving for you having the smaller data set. Another way of looking at it is when you consider traditional machine learning, it tends to be isolated single task learning, meaning that knowledge is not retained or accumulated, and learning is performed without considering the past learned knowledge in other tasks. Okay, so for instance, in a single data set, you'll have the learning system task 1, and then in a second data set, you'll have learning system task 2. Now in transfer learning, it's learning of new tasks that rely on the previously learned tasks. So the learning process can be faster, as I said, more accurate, and hopefully will require less training data. So for instance, you take your first data set, you learn from that data set, you acquire knowledge, and then you transfer it to your second learning task, which is the one you're interested in, from and you can see here just a slightly smaller data set, and this allows you to be successful. And that's this combination of transfer learning and deep learning is definitely what has brought machine learning and artificial intelligence to the forefront in pretty much all scientific areas. So here's a list of what I would term popular transfer learning models. You'll see I excluded some of the legacy early models like AlexNet. I would stay away from the earlier models just because they are just not going to perform as well as the newer models. The classics like VGG16 are still being used, and ResNet 50, but I would certainly consider, for instance, the family of EfficientNet from Google. You'll also see that I added at the bottom vision transformers, so they are different to CNNs, and the reason for that is they don't rely on what we term local filters in order to extract features from the image. They use self-attention mechanisms in order to compute the weighted sum of the features, across the entire image. So they do operate differently than a CNN. Ultimately, the goal is still the same in terms of detection of patterns, but they're slightly different, and they're also usually a lot more data hungry. So there are definitely some pros and cons to both, but there are more and more VIT solutions that are coming out that permit you to use them in a more efficient manner, or with a little less data and less dependencies. So I would certainly look at if you're interested in CNNs, to also consider VITs, maybe do it in parallel, or pilot it a little bit and then see which one works best for you. But ultimately, you need to explore a little bit. I mean, you can do it by hypothesis, meaning that certain models are better suited for certain tasks, but you can also compare and contrast, have some fun and look through the models and see which one works best for you. Now, you remember a few slides ago, we described this transfer of knowledge. So you acquired knowledge from training a first data set, and then you transferred it to the process of training the second data set. So when you transfer this knowledge, if you keep it intact, completely intact, not changing or allowing the change of any of the weights, then this is called freezing. And this is when you retain the weights as they are on all the layers from your transfer model. Now, if you do that, that is somewhat limiting, but the good thing about this is it allows you to keep your data set small. It also needs to be similar to the pre-trained model data set, but it does allow you to have a very small data set because you don't need as much training, because you're freezing all of the weights. But let's say you had a very, very large data set, like really big data set, and the challenge was that it was fairly different from the pre-trained model data set. Well, then you're going to want to retrain by and unfreezing, but you can unfreeze actually the entire transfer model. And when you do that, you're going to tweak all of those weights to best fit your data, and most often you get the best model. But those are probably the two extremes. So quadrant 1 and quadrant 4 on your left figure represents those two extremes. You can then have anything in the middle. For instance, quadrant 2 is when you have a large data set, but the data is similar to the pre-trained data set. Then you train some layers and leave others frozen, right? Quadrant 3 is you have a small data set, bummer, but you have a small set and it's different from the pre-trained model data set, and so that means you train some layers and leave others frozen again. But in this case, you're probably going to have to unfreeze more than, for instance, in quadrant 4, where you're going to leave everything frozen. So this just gives you an idea of how you should approach using the transfer learning technique. And it's very it's very empirical actually, because you're not certain on a lot of things, and so you're going to try it and you can see how it works for you. But very often you will know ahead of time, based on the size of your data set and how different your data set is going to be from your pre-trained model. And that's it for lecture 1, where we've reviewed some key concepts and definitions. And now that they're fresh in your mind, we are going to move on to how to critically review AI/ML publications. We'll see you there.